Okay. So our plan for today, we're going to just take a little bit and get a start on section 3.2. Just sort of talk about the basic setup for how we solve these non-homogeneous second order linear ordinary differential equations. The setup, and then go through one example for how we go through a full solution. They take a bit of doing. There's like 2 pages for each of the examples that we work through, just because a lot of it's algebra. Who loves algebra? It'll feel like regular math, right? Like it's pretty fun. So we'll do that, and then we'll take the rest of the time, which will be most of class, to keep working on the problems on the take-home test. Our plan for Wednesday is to finish this section. And assignment 3, so we're turning in the take-home test by midnight tonight. Assignment 3, I just haven't quite finished writing it yet, but it'll focus on these second-order linear, some homogeneous, some non-homogeneous. Will be posted by Wednesday and due the Monday we get back from break. So yeah, I guess I will just stop there for a moment and see if there are sort of logistical questions. There'll be lots of time for questions on test problems later. The practice exercises come in 2 sections. There's a few from the textbook, and those the pages are posted to Canvas. Just going to double check that. Yeah, so the exercise pages are posted, and then there's another set of non-homogeneous equations just to give us extra practice. Okay. Are we ready to start? Okay. All right. So we looked at the homogeneous equations before, and with the homogeneous just means that this function over here on the other side of the equation is the 0 function. So if that's anything other than the 0 function, is non-homogeneous. And when we solve a non-homogeneous, this is sort of just like when we do the first linear non-homogeneous. The first thing we do is find the homogeneous solution. And a general solution to a non-homogeneous will be the sum of the homogeneous solution and a particular solution. So what we use to kind of help us find that particular solution is called the method of undetermined coefficients, and I think some of the algebra will appear maybe kind of similar as when we do do some integration by partial fractions. Sometimes we use the method of undetermined coefficients to figure out what those numerators had to be. So we start, just like we did with the first order linear non-homogeneous, whatever that function looks like on the other side will kind of govern the basic form that particular solution should take on. And for each term in what we call the forcing function, for each term in the function that's on the other side of the equation, we're gonna have to add some terms that'll be a part of the particular solution. So a lot of the time, that function on the other side really just has one type of function. For example, this is just in 315. It's only a polynomial, so I really want to consider that one form, one type of function to consider. It's possible you might have equations that'll have like a polynomial part plus some exponential, right? And then you kind of have to piece together the parts of your particular solution. And we will see one like that probably on Wednesday. So to solve and find the particular, the first thing we do is solve the homogeneous solution. So what equation do we solve to help us figure out the homogeneous solution? Like, what is it that we have to look at? How do we find solutions in the last section?
Get the characteristic equation.
Okay, so will you turn on your mic and say that again?
Get the characteristic equation.
Yep, leave your mic on. What's the characteristic equation for this equation?
The r squared plus 3r plus 2
Mm-hmm.
is equal to negative 2t squared.
Nope, just 0.
Just 0.
Yeah, when it's the homogeneous, it's always equal to 0. So yeah, we get the homogeneous solution. So we look at the characteristic equation. I think this factors. We have what, r plus 1, r plus 2. We have 2 distinct real solutions. Is this overdamped, critically damped, or underdamped? Overdamped. 2 distinct real solutions. Overdamped. Okay. Now, if those are our distinct real solutions here, what does the homogeneous solution look like? Yeah.
Is that the x equals
Can,
C1
perfect, yeah. So C1,
to the R1 plus C2 to the R2?
yeah. So what is it for this function?
The -1 and the -2 for C1 and C2?
Not for C1 and C2, but for R1 and R2. So like C1 e to the negative t plus C2 e to the negative 2t. Yep. So there's our homogeneous solution. Now we're going to find the particular. So look, the function, the forcing function here, is a polynomial degree 2. So I'm going to start, my x particular is going to start by taking on the form of a generic degree 2 polynomial. So I'm going to have a t squared term, a t term, and a constant. And just, I don't know what the coefficients are. So at squared plus bt plus c. To find what a, b, and c are, I know that when I plug the function in, along with its first and second derivatives, it has to satisfy this given equation. So I'm just going to find x prime and x double prime. And even though I don't know what a, b, and c are, I know they're constants, so we can certainly take the derivative. What's the derivative? What's xp prime?
2at.
Mm-hmm. Plus b.
Plus b.
Yes, thank you. Okay, and the second derivative. Yeah. If you're worried about like beating somebody else, you just leave your mic on, and then you can always be first, right? Okay, so we have our function, we have the first and second derivatives. Now, I'm just going to rewrite this equation. What is it? X double prime plus 3x prime plus 2x And this is supposed to equal 1 minus 2t squared. So now I'm just going to plug in this stuff. So x double prime, 2a, plus 3 times x prime, that's 3 times, I got to use parentheses here, 2at plus b, plus 2x, so that's 2 times our function, at squared, plus bt, plus c, equals 1 minus 2t squared. Now I'm going to expand out the stuff that we have over here on the left side. I'm going to just gather my like terms, defining them by like powers of t. So for the t squared term, I just have a 2a t squared. For the t term, I've got, let's see, 6a plus 2b t. And then for the constants, I've got 2a, 2a plus 3b plus 2c, exactly. So I'm doing some, I guess probably a couple of steps at once here. But what I'm doing is I'm expanding each of these products, like I'm doing the distributing and then combining my like terms all at the same time. And now on the other side, I'm going to write this in a particular way that I hope is helpful. Negative 2t squared plus 0t plus 1. I want to just write the 0t term to help me out with organizing my thoughts. If these are equal as polynomials, right? If the polynomial on the left is equal to the polynomial on the right, the only way that happens is if, well, the coefficients on t squared have to be the same, right? So that means that 2a, so let me go on to the next page. That means that 2a is going to equal negative 2. It means that the coefficients on t have to be the same. So 6a plus 2b has to be equal to 0. And it means that 2a plus 3b plus 2c has to equal 1. Yeah.
On the first line of highlighted stuff there, when the 3 gets distributed through the 2a plus b, is the next line
Oh,
plus 3?
Yep, that's supposed to be a 3b. Thank you. Let me fix that. And then, what was it? 2a plus 3b plus 2c equals 1. Okay. Okay. Cool. All right, so now we have 3 equations and 3 unknowns. We got some low-hanging fruit right at the beginning. A has to equal negative 1. So I get to use that in this equation here. So now I know that negative 6 plus 3b equals 0, or 3b equals 6, and b is equal to 2. Great. So now I know A, and I know B. Throw those in the next one. So if A is negative 1, so then we have negative 2 plus, if B is 3, B is 2, then 3B is 6. And then 2C is equal to negative 3. Yep, so negative 1.5. or negative 3 halves. How's that? Okay. All right, so now what we know is, so A is -1, B is 2, C is negative 3 halves. So x particular is negative t squared plus 2t minus 3 halves. Now we're not quite done. We're getting there. But we know that our solution, the general solution, is I'm going to take the homogeneous and add the particular. And our homogeneous was c e to the negative t, c1 e to the negative t plus c2 e to the negative 2t. And then the particular up here, minus t squared plus 2t minus 3 halves. We're getting closer. We still don't know C1 and C2. They gave us, this wasn't just find a general solution, right? Because they gave us initial conditions. This was an initial value problem. So now what we're going to do is use those initial values to help us out. We know what x of 0 is and x prime of 0. So we need to take this equation, x of t, find x prime of t. Minus c1 e to the negative t minus 2 c2 e to the negative 2t, and then what, minus 2t plus 2. Okay, x of 0, I'm going to scroll up for a minute. X of 0 is 0, okay. So that means 0 is equal to, I'm just plugging 0 into this equation here. So we get C1 plus C2 minus 3 halves. Or, in other words, C1 plus C2 is equal to 3 halves. And then x prime of 0 is negative 4. So negative 4 equals, okay, if I plug it in now, if I plug in 0 to this equation, we get, what, minus C1 minus 2C2 plus 2. And I think that tells us that negative C1 minus 2C2 is equal to negative 6.
Could we also say that C1 plus 2C2 equals positive 6?
You could. Yes, you could also say that C1 plus 2C2 equals positive 6, right? Just if you zap both sides of the negative, or depending on what side you got your terms on. I'm leaving it this way. Yeah, so like you can either use substitution, or when I see these two equations here, yeah, I think elimination by addition. So that's why I wrote it that way. So like I'm just going to rewrite these equations as I've written them here, just one on top of the other. So now if I add them, then the C1s cancel each other out, and we end up with a negative C2 is equal to, let's see, 3 halves plus negative 12 halves is negative 9 halves. So C2 is 9 halves. And if C2 is 9 halves, then C1 has to be negative 6 halves or negative 3. Does that make sense? Does my work look correct? How we doing in Williston? Okay. Okay. Okay, so now I mean, it's all over but the shouting. The only thing, we don't want to, there's not really any more work to do, but stopping right now and not going any further would be like fumbling on the 1 yard line. We want to find the function. Let's put it together. So x of t is C1 is so negative 3 e to the negative t plus 9 halves e to the negative 2t, and then we already know our other coefficients, which were negative t plus 2t minus 3 halves. Negative t squared plus 2t minus 3 halves. Yeah, okay. How's that?
Or how we would solve the last question.
Is the last question on the test a second order? It's a first order? So, I mean, this is, if it's first order, I mean, we still use that same generic, like, approach on some of those, where we find, let me see if I can't, I just want to make sure I'm looking at the right problem. Yes. So it's the same approach because you find the homogeneous and the particular, and you know, use the form of that function on the other side to like get the basic form for your particular. It's just less work for a first order than it is for a second order, because there's only one initial condition that you need in order to solve. So the short answer to your question is, yep, similar,
Cool. All I need to know.
but less work. Other questions?
Can you just go back for a second?
Uh-huh.
To the last page and where you wrote,
Can you, sorry, can you just turn on your mic so that everybody can hear the
Oh,
question?
right, I forgot to do that one.
can you go back to when you did the 2x for the x times x whole time plus 3x times? When you did when you distributed the 2x, how did you get 3?
Ah! Oh, man.
Oh, it's.
Did anybody notice that at the time and not say anything?
I noticed it,
I
but I
assumed
thought
that was right. I wrote it down the other way and then assumed that I didn't miss something.
Oh.
Oh boy.
Well, you know, hold on. So that would be a 2B, right? Is that the only thing that changes on that line?
Jeez.
It's just
I bet it doesn't change everything.
Probably not.
Shows the C value.
Yeah, but let's see. So it's like this A and the B is the same, right? Okay. And then if B is 2, then this is 4. And so we'd be subtracting 4. Negative 1 here.
I thought B would be equal to 3, or to 3, right? Because it would be 2B equals 6.
But that, it only changed, it didn't, that, so the 3B came from this, right? The 2B comes from that. So then this is just negative 1/2. You think so? Doesn't change the derivative.
Yeah, it doesn't change.
That's nice.
Changes everything else.
It changes this is negative 1/2, so that this is 1/2. See, I think it's not going to change as much as we think. It doesn't change the first derivative, so it doesn't change this, right?
Are they trying to say something?
Oh. Are we getting, is there feedback from Williston right now? Hold on. Can you say that again?
So it looks like it is T times 6A plus 2B, one of the terms, and then it's 2A plus 3B plus 2C, not multiplied by T.
Which, so you're up on this line here?
Yeah, shouldn't it be 2B in the yellow?
I think it was 3B because of this 3 here.
But there's no T.
Ah. Mm-hmm. Yep. Okay, here's the thing.
Can we change the original formula?
No, but here's the thing. Originally, I had a 2B there, and then I thought it was wrong because somebody asked, well, isn't that a 3B? But that's because we were collecting so this is 3B here, right? That's fine. It's just that this is actually supposed to be a 2B because of this. This is what's collecting, that we were collecting together. So, so this will actually change. That is a 3B, right? And then this was a 2B. So the devil's in the details. But it's actually, the numbers are going to work out pretty nice, I think. That's a 3. So this is a 9. And that's a -6 here. And that's nicer because then we get -3. No fractions. Phew. And in fact, it doesn't change a whole lot here. It still doesn't change. Oh, it does change actually. If B is 3, it actually changes this to 3.
Yeah, it changes quite a bit.
That's a 3. That is -2t plus 3. Yeah. Changes one more thing here. Oh boy, the devil's in the details, huh? This equation is still good. This equation, -c minus 2c2, this becomes a +3 instead of a +2. So this becomes -c1 minus 2c2 is -7. That changes this. Okay. There we go. This is a -4. So C2 is 4. And if C2 is 4, then C1 is -1. Sharp eye, whoever noticed. Although if you happen to notice something funny like that, if you say it so right away, then like it helps us sort of catch those errors. So then C2 is 4, C1 is -1. So that changes these guys. Negative, and then +4. And then the value for B had changed up there, so that just changes this guy to a 3. And C was -3. That's better. I spent the beginning of class saying, oh, it's a lot of algebra, so it just feels like nice regular old math. But it's a nice regular old math that can still be frustrating sometimes. The thing I like about hard problems where there's a lot of details is sometimes you get to just work them out twice because you realize that you made a mistake and you have to start over. The assignment that you all got back today, or I guess maybe it was Sunday that I put them up on Canvas, those last two problems, I think I worked them each out like twice just to make sure that I didn't make a mistake. And on one of them, I think I made at least one mistake and that like affected my answer. So I feel your pain. I feel like the problems that are sometimes the most fun are also the most frustrating. Yeah.
Did that be end up switching because you put a T at the end of the
You mean so on the previous page? So here's what we did. So start at this equation, okay? So imagine, so what I did to get from that equation, like on the left side, to go from the top line to the bottom, I did like two steps in one. I said, well, what's my t squared term? And my t squared term only comes from that term, but it's being multiplied by 2, so that's where I have the 2a t squared. Then we said, where do our t terms come from? The t terms come from here, which is being multiplied by a 3, so that's a 6at. And here, that's being multiplied by a 2, and that gives us a 2bt. So altogether, we have 6a plus 2b times t. And then we collected all the constant terms. Those are the ones highlighted in blue up there, so the 2a plus 3b plus 2c gives us that. Other questions? Okay, that was a fun introduction. And what I want to do, as promised, is take the rest of the time to give folks a chance to work on the take-home test. If you have the take-home test done and submitted, you don't have to stay. Otherwise, please take advantage of this time, and I'm going to float around the room here to answer questions. And if folks have questions in Williston, just pipe up. I can answer them as best I can, or you could also like message in the chat window or something, or you could text me. You could text me there and even send me like a picture of your work if you're looking for feedback or something.